documenting the front lines of the AI revolution, the AI Rebels podcast.
Hello, everyone, and welcome back to another episode of AI Rebels. I am your co-host, Spencer.
And I'm your other co-host, Jacob, and we have Elija Perrier here with us. Thanks for coming on, Elija.
Thanks, guys. Great to be here.
We're very excited. Elija, who recently finished his PhD, Dr. Elija Perrier, thank you for coming on the show. Are excited to talk to you about all you're doing. You are in a very unique part of AI. For our listeners, Elija has spent a lot of time with quantum machine learning paired with artificial intelligence. He is kind of a renaissance man, honestly. You have a background in law, physics, math, economics, philosophy, like all these different fields, and I'm just excited to see how all of this boils down into what you're working on. So we're very excited. Can you, Elija, on a high level, when people ask you, like someone on the street or your family, your mother-in-law, whoever it is, Elija, what is it that you're working on? What do you tell them?
Yeah, it's interesting because I'm working on several things at once. I suppose the fulcrum concept that ties them together is artificial general intelligence, but sort of at the crossover between classical and quantum computation. So my real interest is in whether and how quantum systems, quantum computing has anything new to offer, some of the protocols around artificial general intelligence, what it even means to learn in a quantum context, what it means to be intelligent, what it means to act. And so my sort of threads, I suppose, feed into that fundamental question. I also have a side hustle in the law, because oftentimes I approach any question with what is new, what is different, or in the law you say what is sui generis, what is something which is new, which emerges. So I have a sort of side gigs where I write academic papers and books on if you change the technology, how does that change the outcomes of the consequences? And then how do governance regimes need to change in response? Yeah, but the current focus is really on the sort of quantum meets AI part.
So what's the goal? What's your vision? What are you hoping? Yeah, with this research, what are you hoping to accomplish or change in the world?
Yeah, I suppose maybe like a little bit of background might give you a bit of context. So I'm from Australia, and I started off my first journey into academia doing law and cultural theory, largely French poststructuralist theory. I was really informed by a lot of Derrida, Foucault, and that kind of thing. I suppose the kind of fundamental questions that are asked in philosophy is really what actually drives me. And the things like, what's the nature of being?
Yeah.
What's the nature of awareness? I then took a side detour to become a corporate lawyer and then banker.
Just a quick little detour.
Yeah, but I always wanted to do physics and math, and so I went back to study that about a decade and a bit ago. And it was really why? Well, the kind of reason was to equip myself with the tools to really pursue maybe the same questions, but with an armory of logic and mathematics and rigor, which, as much as I love sitting along the Seine reading my French philosophical textbook, it just lacks the rigor of modern scientific logic-based approaches. And so
Foucault is not known for his, historical accuracy all the time. I love him as well. But
no, indeed, totally triggering. I mentioned like Foucault and Derrida to a few people, and they're totally triggered. Although I was chatting with a UCL professor the other day who's not triggered by. He's like a comp sci professor who advised on on some films and AI. But just to answer your question, then, so these are driving questions for me, and so I suppose, like a lot of people, they thought, well, if the goal is something like maximizing understanding, then you sort of think, well, what structure in the universe could maximize information or maximize knowledge or understanding? And really, it actually ties back to a lot of early concepts. Not just early; these are concepts that have been around for a long time around the role of knowledge and learning and self-realization. So the romantics. So I did my first thesis on this. The romantics of the 17th century would often take an idea and say, well, we have this dialectical process by which we reason and learn to know, and by knowing we reach some sort of enlightened state. In ecclesiastical context, it's you become closer to God. In more sort of scientific context, you become more aware of the universe. And so that, I suppose, is where my interest in AGI and AI came from. And then if you believe in quantum mechanics, you probably should, then there's this question as to what, I suppose, the most powerful or most informationally fulsome structure could be. And if our assumptions are correct, then it would be a quantum computer. We think, we're not sure. And so, anyway, the kind of intersection of those philosophical questions is then at the intersection of AI and quantum, and that's where I am now. So that's a long-winded answer.
Yeah, I was going to comment. A lot of this stuff kind of feeds into each other. I mean, Foucault and Derrida, like post-structuralism is kind of an influence on a lot of the philosophies that inform AI. Do you think that was intentional on your part? Was there an underlying interest in AI that kind of guided it, or is it just all kind of serendipitous? You had a lot of interest that ultimately ended up aligning with the modern deep learning model.
I think it's probably the latter, because I for me, the skeleton key between like physics, mathematics, logic, computer science, philosophy, law, and economics is logic, or that sort of, you might say metaphysics, but you have to write metaphysics down in a language, and so because you're writing it down in a language, you're subject to the logic and the laws of grammar of the language. So that's the sort of fulcrum point. But I hadn't ever really considered the nature of learning. I wasn't familiar with Shannon entropy, for example, when I was studying Derrida. Shannon entropy is, if you study information theory, is pretty key. So, yeah.
So, what quick definition of Shannon density? Is that what you said? I apologize.
So in the kind of quantitative sciences that study the nature of information, how you measure information, and how you measure the effectiveness of communication, was largely developed by this researcher named Claude Shannon. I think he was, from memory, it was something like a code breaker. He worked, I think, during the war on on encryption and so on and so forth. But he and others, but essentially Shannon, came up with a way to say, well, how do you measure the amount of information in a sequence, or in a statement, in a sequence of strings strings, in a communication which you send or has been received. Now, part of why he was kind of interested in that is if you can quantify the amount of information that you input at one end of the line, and that number changes at the other end of the line, you know that the channel, the pipeline, according to which you've transmitted, has done something to the information. Either it has failed to stop the information from fraying, or maybe someone's eavesdropped on your wire. So that was the problem he was trying to solve largely. But it turns out that measure of information is very much aligned with entropy, and entropy is a measure of order in the universe. It's the sort of basis of thermodynamics, and I've actually got a paper which is coming out on arXiv, I think, in the next 24 hours on that. But
oh, nice,
awesome!
Yeah,
we'll boost that.
Yeah, drop a link for that.
And and I should say, Shannon entropy. So modern quantum. So if you go to university, or maybe go to a lab or whatever, and you say you want to study quantum computing, if you get into the theory, it's really quantum information processing. And so you actually realize that there is a bit of an isomorphism, a way of mapping between like theories of computation and like what's going on with quantum circuits and information channels. And so then again, this is, I won't go into it because it'll take too long, but when you observe something in the universe, that actually is framed as a quantum channel. So measurement is framed in this language of information theory. So there's a really nice synthesis of information theory, quantum mechanics, and computer science in quantum information. So and understanding entropy is key because it's key to quantum computing.
Right.
Yeah.
So I remember
I'll be ranting.
We had Michael P. Frank on here a few months ago, and he was talking about reversible computing, and he was mentioning the same thing. He's a reversible computing guy, so he's a little bit bearish on quantum, but I'm sure you and him can have that out sometime. it was
Yeah.
really interesting to hear about the problems that end up occurring with information and data storage when you get down to a small enough level and start packing too many transistors in or whatever. I can't remember the term right now.
Yeah, well, there's this one of the many interests in quantum is that essentially for classical computing, as you make chips smaller, you're concentrating a lot of energy into a smaller space. And so as you're doing that, you're increasing the entropy of the system. And at a certain point, it becomes so much energy into the small space that the actual circuits, the actual physical motion of the objects that are doing the computing starts to become too noisy. And so one of the, I think this is well established, one of the key benefits, if we can build one, of a quantum computer is that you can essentially leapfrog that thermodynamic barrier and have these computation occur at a much smaller level, but at a much lower thermodynamic scale. And so essentially Moore's law hits this thermodynamic barrier, but if we can build a quantum computer, we would have a quantum leap and keep on scaling our compute. So yeah, it's a biggie.
Wow. No, this is huge. Can we? Okay, Spencer's more technical than I am, so I'm the real person you're going to have to help understand here. But can we dig into like the research? What is it that you have been working on and continue to try to push?
Yeah, a whole bunch of things. I mean, I finished my PhD thesis is called quantum geometric machine learning. So I always like to let's break up each of those words. The quantum bit refers to quantum computing. The machine learning bit refers to learning algorithms that are running on systems that satisfy the axioms of quantum mechanics, quantum information processing devices. The geometric bit is focused on using techniques from geometry, largely the same sort of math you see in general relativity, to solve problems in quantum computing. So what does that mean? Well, one of the features of quantum computing is that the computation, when you write it down, or the actual way that a computation unfolds must satisfy certain laws of physics. It needs to satisfy symmetry properties. So that means that you have to ensure that the system changes and evolves in a certain way. This is very unlike classical computing. Classical computing does not have to obey these symmetries. If your system does obey those symmetries, it will retain its quantum characteristics. And that's where the secret sauce is. Essentially, that's where you get this sort of power of running quantum computers. It turns out that you can actually conceptualize a computation on a quantum computer as taking a walk on a landscape. These landscapes, it's a manifold, and the manifold is what's called a Lie group. I won't go into that. But basically, to do the shortest computation, you want the shortest path. Just like, if you're walking down the shops, you don't want to take some route out back and beyond. You just want to go straight to the shop, right? And in principle, the shortest path should be the lowest energy path as well. And so when you're trying to work out, with classical but also quantum computing, there are often two things you kind of focus on. Does there exist a computation to get me from A to B? Because we know from Turing that for some problems there is no computation from A to B. Like you just cannot get from A. If your algorithm doesn't hold, you will not get to B. But sort of if you ignore those pathological examples, then you want to say, does the computation exist, and is there a shortest path? So if you're on the top of the Earth, there's no single shortest path down to the South Pole, right? There's actually an infinity of paths, but there is a shortest path from like the North Pole to New York, for example. So what you want to do to have the most efficient use of energy is to estimate what the shortest path is for your computation. And it turns out that, well, finding the shortest path is not unlike the way that objects move in space-time. So when an object is subject to the force of gravity, what's actually happening is it's following the shortest path in curved space-time. And so it turns out that you can use these similar mathematics to try to estimate what sequence of pulses and buttons you may need to press to make your computation follow the shortest path in this computational landscape. So that was what my PhD was on. But I also, again...
It was on how to do that, or what that...
Yes.
looks
Yeah,
like how to
yeah.
do this, how to
How
create the
to do
shortest
it.
path for this quantum computing to
Yeah,
ensure the lowest amount of energy is
correct. Yeah,
this. Okay.
yeah. Because one of the things with machine learning, at least sort of classical ML, is you often use it where, say you have a workflow and there's some part which is uncertain, then oftentimes that's where you inject the ML. So for problems to do with computation, it's really what's called a control problem. I can control, like I'm at my keyboard and I can control what I type in and I can build the algorithm, or I can or it's sort of like I'm driving a car and I can control the car by using a steering wheel. And I want to know what's the optimal sequence of like turns of the steering wheel and presses of the accelerator and the brake to get to the endpoint. And mathematics and the sort of theories of geometry and so on that were developed maybe 100 years ago can tell you a lot about how to get there, but they don't necessarily tell you what the sequence is. And so that's where machine learning can come in. And so my PhD was saying, how do we introduce, I started in 2018, things are a bit different. How do we introduce basic, I think I was using GANs and it's a basic deep learning techniques to learn that sequence. Yeah. So, but since then, very quickly what I've been doing. So I've got a work stream on, this seems disconnected, but it's not. The first work stream is on AI risk. So I have a bunch of papers on how you wrap quantitative risk modeling around AI. If you study AI, or if you're just into it, which a lot of people are, there's a whole world of trying to evaluate how these models behave. Is OpenAI's latest model, is it, it's going to kill us if it exfiltrates onto some other server? Does this model from Claude exhibit collusive behavior? Does this model from Mistral fake alignment? Does it act like it's aligning, but secretly it's not, right? And that's all important research, but oftentimes that research lacks a sort of background in sort of empirical scientific experimentation. It's not a criticism of the people doing it. They're incredibly bright people. It's just oftentimes there's not the sort of background of, well, how do you analyze the risk? And risk is a very well studied and understood tool and thing in the universe, and we're all still here. Businesses are still around. We haven't killed ourselves with nukes yet, partly because we have ways of managing risk. And so I've just got this basic work stream because I was like, so I have a background in data science when I worked in politics, and a lot of it is really trying to calculate risk. And so I sort of I have one work stream where I'm writing papers on how would you bring existing risk techniques to quantify the risks of AI. So just to give you an example, it sounds obvious, but it hasn't been. Someone may have done it, and if anyone watching this tells me it's been done, please tell me, because I'd rather not write papers that have already.
Rather read one.
Think of anything you're doing a task. In my paper on scenario modeling and AI risk, I say, take a logistics company. It does three things. Someone wants to click on something they want to buy. It has to work out where to store it, and then it has to get the package from the warehouse to the person, right? Basic thing. And so currently, if you work at Amazon, there are people whose job it is to manage risk. They will say, what's the failure rate of that first bit? What's the failure of the second bit and the third part? Right?
I see.
And they will use that, and it's the same with anything. They will use those existing models to then try and calculate how do we reduce the risk, so on and so forth. Well understood, well practiced. The world functions on that. If it didn't exist, we'd be in trouble, right? So my basic contention is, as I said at the start, when you introduce anything new, you sensitize. You say, well, so if I'm using AI to do this, what I'm really doing is I want to have a benchmark which says, if I do the thing not using AI, what are the risks? These might be the risks of catastrophic failure. They might just be the risks that something breaks.
Yeah.
And then if I add AI into the workflow, as in I change this input, how does this measure of risk change? And so that's one.
Yeah. No, that makes total sense. I think that's crucial. It's similar to what comes to mind are a few examples, but one, it's easy to say, for example, self-driving cars, right? That use AI, self-driving cars, to expect perfection. Well, no, if it's better than humans, we should, what is the risk of introducing self-driving? Does it actually decrease the risk of a crash by introducing self-driving, or does it increase it? Because if it does decrease, even if it's not perfect, it might be worth using, which is different. But I think it's just this idea of risk. Yeah. Go ahead, Spencer.
Well, I was going to ask, do you view your efforts in quantum computing as kind of a key part of this risk assessment initiative, if you will? Do you think that like the quantum computing is critical to being able to map these risks, or do you think it's something that can be done with classical computing, just not with the particular thought paradigm that other people are using?
Yeah, I mean, I think to answer that question, we have to take a step back and say, what does quantum computing bring to the table?
Yeah.
So,
Yeah.
so we exist in a classical world. We only can exist. I mean, we can have interesting philosophical debate, but really, we only exist in the classical world. We represent what quantum computers do can only be represented classically. That's why we use probability theory. And so even risk is subject to this classical representation.
Right.
And so what does quantum bring? Well, in principle, if you solve error correction and a bunch of other problems, let's assume that we have solved that. Then what quantum allows you to do is, in principle, all computable functions can be computed with it's just that some may require exponential time. It may take so much time and resources that you actually couldn't do it. And for certain classes of problems, we believe quantum computers provide an advantage. As in, they can complete that problem that a classical computer would take an exponential time in a polynomial amount of time. That's what it means to be tractable. And so then in principle, there may be problems like the traveling salesman problem. Someone might shoot me down on this on comments. But there are a class of problems which may look like risk-style problems, which perhaps a quantum computer can give you finer-grained analysis. So one of the mooted use cases, I'll give you an example, of quantum computing is quantum chemistry. Why is that? Because in quantum chemistry, in any quantum science, you write down what's called a Hamiltonian. The Hamiltonian is a mathematical description of how the system evolves over time.
Mm-hmm.
It's a representation of Hamilton's equations, which are what are called equations of motion. In principle, you can write down what one electron's doing and then what another electron's doing, but because they interact, you need to write this third term, which is like an interaction term, and that's just two electrons, right? So as you start to add electrons, basically you cannot do the computation. So I spent 6 months doing 1 2-qubit classical simulation of a quantum system part of my PhD. It literally took 6 months to do the one computation. I didn't have Facebook's resources, but even if you had all the GPUs in the world, if you add a few more qubits, a few more electrons, you're basically stuck. So one of the promises, and this was Feynman's point, but also the Deutsch Church Turing thesis, is really that if you want to simulate a quantum system, you need a quantum system to simulate a quantum system efficiently. And so maybe that, but to your question, Smith, maybe that would assist, because maybe you can then say, well, this quantum algorithm allows me to leverage the power and enhancements of quantum computing to more finely calculate risks, but it's very uncertain. So
that it's funny that you mentioned the traveling salesman problem, because that's actually exactly the example that I had in mind, which is at least, and correct me if this is an incorrect interpretation of what you're telling me. So I'm imagining quantum computing is essentially being able to classical computing, you're in the grid itself, you're having to traverse the grid and figure it out. It's essentially tree traversal or whatever, right? But I imagine quantum computing, you can kind of zoom out a bit and map out before you make your moves. Is that very crude reduction?
Yeah. So for anyone who's tuning in, that the kind of, if there's one place to ever get your quantum info fix from, it's Scott Aronson's blog, and the kind of big warning sign in his blog, or at least it was there some time ago, is like quantum computing is not just parallel computing. So there are several classes of quantum algorithms. There's like a quantum version of the Fourier transform, the quantum Fourier transform, which is essentially essential in certain algorithms to do encryption. And then there's what's called quantum search, and so quantum search can give you a speed up. And then there's other discrete logarithm problems. So there are all these classes of algorithm which we believe give us some speed up. The speed up doesn't necessarily shoot us into this higher order complexity class of problems that we can solve efficiently. But if your search is root and faster, that's a good thing. So these algorithms. So in principle, if you can build a quantum computer, in principle, you should gain some benefit. Again, a nice, set of nice assumptions, you actually could get benefit for a whole range of algorithms. People who would be commenting on this now would say, well, hang on, you need to prove that there's no classical algorithm which could give you the same benefit. And that is true. So it's not actually true that it's been proven in an ironclad way that the complexity class of problems that can be solved on a quantum computer, that there does not exist somewhere in the universe some algorithm that could solve it on a classical computer efficiently. We all believe that. Like, we believe that BQP is a subset of B sets, that these complexity classes have a hard boundary, but it's very hard to prove the negative. So
fascinating.
I'll
to wrap your mind around.
Very quickly, I thought maybe some of the other stuff which you might find interesting is doing a lot of work on theories of computation and transformers, and that's in the context of language model agents. So me and Mike had a paper for ICML. We'll see if it gets up. Where we're just drawing attention to the fact that there's this gung-ho drive to agentic AI, but that actually, if you look at the math, it's kind of obvious, but sometimes you need to write these obvious papers. The actual foundation of most agents is a language model, and language models have these, what I call, language model pathologies. They are stateless, they are stochastic, they are linguistically intermediated. And what this means is that we are talking here, and I'm sure if I saw you in a couple of years, although you've grown a bit, maybe you have a longer beard or something, you will have retained your identity largely because of the persistence of your physical bodily form. But that's not the case with language model agents. And what you see is, for example, as you increase context length, so people don't even see this, if they're on GPT or Claude at the moment, as your conversation gets really long, some of the answers start to fray a little bit. Some of the accuracies may be fray. So although there are great strides in context length and so on and so forth, there's not this embodied substructure which you can anchor the agent onto. Now, that's kind of obvious, and sometimes you don't need it. You just need an agent to book your flights, who cares? But if reliable persistence and continuity of an agent is an important thing for you, then you will not get it with an LLM. So that's why we build these whole architecture around them, like tools and scaffolding and rags and so on and so forth.
And even with that scaffolding, I've done a lot of playing with AI agents of my own. I built one with a little meme coin around it just for fun.
Yeah, right.
But I at one point I showed him the charts of some rival coins, and Chill Guy was at the top. And from there on out, for a while, he was really fixated on Chill Guy, and he hated Chill Guy. Like, he would just constantly tweet about like how Chill Guy needs to be destroyed. And I finally just had to go in and I had to just wipe his memory so he would stop talking about Chill Guy.
Yeah, totally. And what is interesting is that dynamic you described is, oftentimes, in AI research and alignment research, all these problems have a very similar structure, and they may even actually be the same problem on alignment. But the kind of fact that this agent is starting to hate on this other Bitcoin, and it's just like totally throwing shade everywhere. Like, it's actually it is in part developed this kind of instrumental goals, and this reward signal is being generated. And so there's a lot of interesting work. Dan Hendricks has a free book on it if people are interested on sort of intro AI safety. But there's a lot of interesting work. You might jump onto Less Wrong and blogs like that around how, like, the kind of thing that the reason that behavior emerges is because of actually the nature of the computational model sort of underlying it. And you see this a bit with like reward hacking. So, other types of behavior that we see in models. So, it's important just to be aware of this. I use LLMs every day. It just totally accelerates my life. I don't.
Yeah.
They're not perfect. I'm sure you guys do too. But
exactly. Like, you have to be familiar with their failure modes. In order to use them properly as tools.
Yeah, and coming back to the risk point, me and Mike got this paper. We didn't get it done for ICML, but it'll be coming out soon. Which is, how do you wrap that risk artifice around agents? So, how do you quantify their failure modes?
Interesting.
How do you quantify, like, I'm using this RAG structure and like this tool palette to solve some. Maybe that's not the optimal. Maybe you want a different configuration. because the failure modes of chain of thought or something are less. So we really don't have the science of AI risk at the level yet where we can calibrate and really understand what the costs and benefits are of these different configurations are. And it's important because if everyone from JP Morgan down to your little old lady down the street is going to be using agents, it's really important to at least have a bit of a read on what configurations
Yeah,
may or may
yeah.
not work.
Well,
So,
I mean, along those lines, you have maybe more than anyone have you spent a lot of time with this AI risk structure, and you've thought a lot about it. Obviously, you've dug into it. Where do we stand? Like, what is the risk, in your opinion, of integrating AI into our lives? What's that differential risk?
Yeah. Look, it is hard to quantify. We don't have the data. So one of the papers I wrote was, well, how do you quantify something that you haven't seen? And essentially the answer is you take an educated guess and then you use something like a Bayesian update rule. Essentially, you learn. To answer your question, I think, there's a billion risk frameworks out there. And my view is the kind of two things are, again, we in society manage catastrophic. Let's just take this kind of thing that people think is so kind of sexy, catastrophic risk. We manage catastrophic risks all the time, and we have a well-trodden pathway, a nuclear plant. We can't control the fission process, but we wrap scaffolding around it to control everything that we can. We can't control turbulence, but we build control architectures to manage the risk of of turbulence. So we also don't fly into hurricanes unless you're a nutcase. So we have tools and a set of behavioral protocols. So I think that fundamentally has to be how you approach any risk. And so that applies to the obvious use cases where, like, if you've somewhere in a data center in the next year or two, who knows what, there's going to be such intense computational pressure on training models that OpenAI or maybe Anthropic, I don't know. Let's say that the kind of top candidate for AGI style AI is probably OpenAI. Maybe there's a basement in China building it, I don't know. But let's say it's OpenAI.
It's possible.
There's all these pressures there. So the question is, well, so what if this unusual thing emerges in the basement of OpenAI? It only matters if it can influence the world. And so again, building control architectures around high risk, highly intense processes is important. But the other thing I think is this cumulative risk and attrition. Just think about the average person's using large language models to draft, say, first drafts of XYZ. And that LM goes onto the internet, and the internet's been totally shitified by other language model content. So you have this like confounding problem that the language model is quoting other content from the language model, and it's essentially but that cumulative risk is something which I think is really important to be aware of. That it's like Chinese whispers. If I'll tell you a story, there's a little bit of misinformation, and then you will tell Spencer, and then Spencer goes and tells someone around the corner, and that cumulative risk, particularly when you have AI agents talking to other AI agents and getting stuff wrong, but it's happening kind of almost,
that's terrifying.
At very close rates. That's something. Sorry, that's the
What I found interesting about observing AI agents interacting with each other is, in a way, you can kind of see like a very exaggerated version of what you were talking about with like the human tendency to, telephone and sort of slightly change details. 'Cause, you're looking at, I do this with AI agents of my own. I'll just spin up a couple on my Mac Mini and then, go into Discord and have them talk to each other. And they have slightly different things in their context to start with, and so whenever one of them says something that's vague in some way, the other one takes it in a completely different direction. And it's just it's fascinating to see, and then it's also fascinating to like you're exploring, consider the downstream effects of it. I was going to say with the paper that you're writing with Michael, is this focused on like a sort of like an eval framework approach to figuring out the risk?
Yeah, it's called agentic identity evals, and it's really so I have all the simulation. I'm doing like my old supervisor used to chew me out for doing like too many things at once, but I'm finally coming to this sort of like point of convergence. But yes, fundamentally, it's about a series of techniques to evaluate the nature of agentic identity. Just asking this, but is the agent you started with at 9 a.m. the same agent you end with at 5 p.m.?
that's
or
interesting.
in 2 weeks. Again, whether that matters is totally contextual. But there's a lot of cases where it will matter. And so it's about trying to provide a framework, and it'll be open source, that people can then maybe build on to wrap their own analysis in, to really just understand what they're getting into a little bit. So so there's that work stream that also then feeds into some of the stuff that Mike and I will be doing on quantum AGI, as well. He's got some really interesting work that we're going to apply it to.
So I'm curious. I have to ask this question. And I'm going to sound like a pretentious philosophy boy for a second, because it's just itching my philosophy brain. So with agentic identity, sorry, what was the last? Agentic identity evaluation.
Yeah.
My brain is not keeping track of words today. Anyways, ontologically speaking, like, how do you define, like, what is the identity of the agent, and how do you measure it against the later new ontology, and how do you define?
This is I suppose coming back full circle to my own interest. The thing I've studied most is the nature of identity in philosophy. And David Lewis, the philosopher, says there are no problems to do with identity. That actually identity is black and white, Leibnizian identity. All you're doing essentially is comparing one representation with another. He doesn't say that bit, but essentially his counterfactual possible worlds analysis is essentially all premised on his idea that there are no genuine problems of identities. In chapter 4 of his counterfactuals book. So to answer your question, Spencer, so fundamentally, maybe build some intuition, maybe for people watching, it's like to be identical is to be the same, it's to remain the same. And so we have ways of assessing when a representation or thing, something we measure, is the same. So take a language model. If I give it a prompt to instantiate it, like you're a lawyer or something, and I ask it a question to do with its attributes. Are you a contract lawyer or something? In the most identical case, it'll just literally come back with the same answer. So, as in something which is constant that doesn't change over time, is in some sense it's like sort of pure representation of identity. And then what you're trying to do is you're trying to measure difference. That is the nature of all measurement. So what you're assessing is, well, how do we identify? And it raises fundamental ontological questions, because how do you identify an agent? Does it even matter if you call it an agent? But fundamentally, I think we have the tool. One of the interesting things about and embeddings is, in some sense, we have this kind of mathematics now. We can wrap numbers around qualitative estimates of how similar things are.
Yeah.
So I don't have to say, well, dogs and cats are similar because in my mind they got like legs. I can check the cosine similarity of those embeddings. People have debates about whether that's appropriate, but we have ways of measuring identity. And so part of the evals program is really trying to explore some of those techniques. There's it actually draws on philosophy. There's diachronic identity, which is identity over time. Synchronic identity, which is identity at the same time. And, So, and then there's this whole question of identity in quantum mechanics, which I won't go into.
Oh my gosh.
There's another layer.
Layers on layers. So what you're trying to do is build this framework, an open source framework for organizations, individuals to use to be able to quantify their agents' change. Am I saying is that at a high dumbed down level?
Yeah, and look, all things change. So at one extreme, if you have an agent, let's say you have a nice definition of an agent. There's lots of debates. Let's say that you sort of have this definition of an agent. If the agent doesn't change, it doesn't do anything, it's not really useful. If you have an agent that changes infinitely all the time, you probably couldn't even call it an agent, right? So there's two extremes. You don't actually have this concept of agency. Sort of agency only exists in this sort of fuzzy world where things remain the same enough, but they also are able to differ. And that's just like us. I was going to say, I was
just like humans.
Totally. And so, but I can measure your height, and if I come back tomorrow, it's not really going to change. I mean, maybe if I measure in the morning, it'll be different from the afternoon. But basically, there's whole range of things about you that aren't going to change. Your personality, you may be in a good mood, maybe I'll get you tomorrow in a bad mood, but over time, I try to work out whether I could probably get a pretty good read on personality characteristics, and they're pretty stable. They are not pretty stable when it comes to language model agents, and it's not a criticism of language model agents. They're amazing, but their versatility is a double-edged sword, and so being able to quantify that to in some useful way is really what the program's about.
It'll be really interesting to see, within this paradigm, it would be interesting to see if there are kind of different rates of change, essentially, that different industries settle on. Like, say like an AI music music production agent probably should have a slightly higher rate of change than, an accountant agent, right? Like,
right.
Totally. So look, really, we have had a lot of interest. We haven't even put out the evals paper. We've definitely had a lot of interest. On the risk front.
I mean, I can think of endless uses already for the eval framework. Like I have talked about this many times with people that, like, if you can get an eval framework that effectively evals agents like that, then you have an effective agent.
And you can actually do something about it, other than if you're just like shooting in the dark until you can actually evaluate and here's where we're at and here's where we want to be.
Totally. And look, there are evaluation frameworks for aspects of agentic sort of activity. There are frameworks for evaluating how sort of robust chain of thought sequences are, for example. But there's not this sort of, again, this wrapping of, I call it risk analysis, but risk could also just be called like identity and difference analysis. To sort of show how these. So I think of these in terms of physics. In physics, you're concerned with position, and then momentum, and then rates of change to the point you made, Spencer. So how do you, in physics, you have a frame of reference. I observe an object. I then take another observation that gives me a way to assess the rate of change. And then I have a rate of change of the rate of change, which is like acceleration and so on and so forth. So there's actually a very well-trodden formula and approach in the physical sciences to estimating rates of change and identity. And hopefully we can make a contribution.
Sounds like you're the man for the job with your Renaissance man background. You can bring it all together.
It's interesting you say that, because I just finished a paper it was a small extension of one of my PhD papers. So I finished a paper in about a day, and I sent it up to arXiv last night, and it was just on this sort of highly obscure mathematical problem in control theory and group theory, and I sort of turned it into a machine learning problem. I had intended to for my thesis. I just never got around to sort of actually putting it on paper. And I was very able, I use language models. I said, well, here's the theorem. Can you just build me a simulation? I was very quickly able to, I had to tweak the code, but I was very quickly just able to run some basic simulations to show that the machine learning model actually worked. So, I saw someone commented on LinkedIn or something that if your level is 0, it won't help you get much above that. But if you have this multidisciplinary background, language models can very quickly help you join the dots. So, you still have to check what they do.
Yeah, definitely.
No, I think that's a very common. It's a shared commonality across, I think, most of our guests so far, is that almost all of them have had very eclectic backgrounds in a lot of different areas. And that's enabled them to use LLMs in a much broader way than other people, because, as you said, a big problem with LLMs right now is, you can't necessarily always validate the information right away. And it's gotten a lot better, but it still hallucinates, right? And if you don't have expertise or even just experience in a particular area, you're going to have a much harder time spotting those hallucinations. Because even if you don't, once you have a really broad base of knowledge, I think that it helps you, because even if you don't necessarily have experience in a particular area, you start to learn to be able to learn what to look for and what might indicate, a misleading answer or hallucinated answer. It's fascinating. Do you think that for the time being, do you think AI will continue to mostly benefit the generalists, or do you see something coming for kind of specialists as well? If you had to put on your prediction cap.
I heard an interesting soundbite the other day that if you rank people by education level, actually, Chat GPT use was higher among more sort of lower educated people than higher educated people. So maybe this sort of inverse Kruger effect,
Yeah.
where people who are more educated are more circumspect, or maybe they just don't trust it because I had to do a degree to do this, so there's no way I can. So whereas
Right.
if you're coming from, one of the, it's we used to think about this a lot when I worked in politics. In politics, my job was as a data scientist, so I used to have to essentially score people on how they vote, and so we would try to predict how people vote, and then that would then get fed into the campaign decisions. And this is very crude, totally unscientific. But one of the things I was always at pains to stress is, never underestimate the role that, and it's partly informed, I guess, because my dad's a psychologist, but the kind of role that shame plays in people's feelings if they have a low level of education and they encounter, a workplace or others where people do have high education. It's different from, I came from a poor background and whatever, we didn't have a nice house, because it's something much more core. I think it's actually, if we can get the guardrails right, I actually think it could be such a tool for social mobility for people that haven't had the opportunities, but also have this emotional feeling of, I'm nothing because I wasn't educated. I didn't, I didn't go to Stanford, so I didn't. So I'm sort of hoping that it goes down that way, sort of route.
Yeah.
So
we talk about that often. It seems like, how AI, I think that's one of the greatest. I mean, obviously we love AI. We're on this podcast, but I think one of the greatest things it does is that mobility, where it truly allows a motivated individual to accomplish what they want to do. And I think now it's less so innate talent, it's more so motivation. I think that distinguishes people.
I could not agree more. I often, I'm a bit of an evangelist in the sense that I say to people, look, it's so easy. You just get the app and you can really quickly up to it. But one of the problems is, again, that skill of being motivated is itself something that's partly learned. Like if you're from a family that hasn't had the opportunities, and someone's like, here's the Oracle, people wouldn't know what to do with the Oracle. I mean, they might ask it, who's going to win the next sports game? But they wouldn't know that, because, well, okay, maybe I could very quickly get into finance. I mean, suddenly I'm working at a hedge. Not that you want to work at a hedge fund, but I'm just using that as an example. So so very cool.
Yeah, no, it's very exciting. I think there's a lot that is going to continue to change. I think people think this is what AI is. And I mean, agents already, we're seeing so much shift there. I'm curious, Elijah, as you are so deep in the workings, the backbone of AI and how it works, and you're doing all this research, is there something that you kind of foresee coming down the pipeline that maybe people like me, more generalists, maybe aren't anticipating?
I think, look, you would have heard signals. So I was at this, in October, I was in Santa Cruz for this, there's this group out of Berkeley named Far AI. They do a lot of great work. This venison alignment research guys. They had a really good, there's a lot of these catch-ups, but they had a really good alignment workshop down there. And, they had people from OpenAI, Anthropic, Google DeepMind, and other labs. And the single serious point they were all making is they thought that AGI was coming very quickly. Now, there's an interesting whole debate about that. But even if you put aside whether this AI is AGI, the fact that they were saying the self-learning, using models teaching themselves, essentially AI research is being done by AI. We're at this, it's not even a hockey stick. It's like this, I don't know.
Vertical,
maybe it's maybe it's an ice hockey stick. It's insane. So I think that's the case. But I think maybe the two things. So I've got this. It's not my idea. It's been around for a while. But this energy barrier. So I've got a paper coming out shortly on arXiv. It's called "What's Per Intelligence," and it's really just trying to put a bunch of mathematics, very very simple results around how you might quantify the the efficiency of intelligence run on different hardware.
Mm-hmm.
Someone may have written this paper already. Please send me your hate mail or whatever. Tell me that it's been written. Basically, so it's about this barrier. And then the second paper is really around the role of catalysis. So, which I'm hoping to put up on archive later this week, probably on the weekend. So what that's about is in the natural world, there's a bunch of chemical kind of processes that shouldn't occur. They're just not energy efficient, right? But it turns out that the geometry, I don't know if you've had anyone on talking about this, but the geometry of enzymes, for example, means that they can perform chemical operations which would otherwise just take too much energy or would just take too long. And they're fundamental to life. Like there are very few intelligent systems that lack enzymes. At least that's my understanding. So catalysis is about framing it as a what's per intelligence point, that it's about energy efficiency, but in a way that doesn't require too much energy. And so I think that I could be wrong, but I think until we design the hardware with catalytic properties, like we can design smart algorithms. In a sense, that's doing catalysis. Like, I found an algorithm with fewer steps to do the same thing. I've made it more efficient. If we can find catalytic structures for artificial computation, then we may see what GPUs were for CPUs, but on a much greater scale. Why am I confident in that? That is how life unfolds. So I'm really excited to see whether we can synthesize some of that research with maybe some of the findings from AlphaFold to see, what catalysts can the AlphaFold program reveal, and how would you engineer those into a circuit or a chip, and then would that help you scale up beyond the current barriers? So that's probably my one recent focus. I think maybe the other thing is we have to have embodied intelligence, just from a bitrate perspective. I kind of a little bit agree with Jan LeCun. I believe in the linguistic turn or the computational turn, as they describe it, but I think until we have embodied agents, they won't have the online feedback.
Yeah, that makes total sense.
I think Alex was talking about that yesterday as well, I believe, if I remember right.
Yeah, I think so.
We had another guy on yesterday who was talking about that exact topic for a while.
I would love to know. I feel like someone's already written this paper.
I don't know if he's written a paper on it. I'm not sure. But he talked a lot about how he thinks that there needs to be embodied intelligence.
Oh yeah. Definitely.
Yeah. No, and I agree as well. I think that, to me, it seems like Jan has gotten a little bit too copy about, language models. He seems kind of mad about them.
Totally. It's like him.
But
him versus the rest of Twitter.
But I do think he still has a little bit of a point with his whole house cat is smarter than an LLM, and it's it's not, but also I see what he's saying.
Yeah, and again, coming back to, and Mike's got some work on this. This is partly what we're trying to integrate, but from an information theoretic perspective, look at how intelligent life humans, there are certain parts of us that are highly robust to change. Our DNA doesn't really change. Yes, you might be unlucky and something, and as the RNA is synthesizing, there's an error and you get cancer or something. But our RNA, the kind of site of intelligence, varies depending on how robust, how variable those structures are. And it's right. So again, coming back to the point I was making to do with agents, if we were just constant, we wouldn't be alive. If we were changing all the time, we wouldn't have any structure or cells. So there's this interesting multi-scale level around the degree to which subcellular structures vary but stay constant, cells vary but stay constant, organs vary but stay constant. And I suppose it's the sort of same process as you go up the ladder of life. And so we don't see that with language models. Simply, they're hard-coded. Once they're trained, although we have a lot of amazing stuff through inference, they're essentially hard-coded. Weights are not adapting, and so this question about activity is, I think, central. So,
wow,
awesome!
It's a wild world we live in.
I love that.
What's going to happen in the next month or year,
next week, even.
Yeah.
It's crazy. I sort of, I mean, I'm sort of in the middle of slowly moving to the States, actually, and although it seems like in the other direction.
Come on over.
Yeah, no. I can't wait to sort of be there permanently. But yeah, I think so. So I do a bit of work at an institute here called the Gradient Institute, which is like an AI safety research group just across campus here. And the guy that runs that's always like, until there's a catastrophic event, like people they
Don't care.
Yeah.
Yeah.
So
it's just not tangible. They can't imagine. You really can't understand it. Yeah.
Yeah. And I suspect it'd be always place it better on incompetence for failure, because it'll be someone doing something they didn't even intend to,
Yeah.
some
Totally.
back end person doing something,
hits the wrong button and sets it loose on the world. Yeah.
Let's just erase all this Fortran code. It's so old. Suddenly the financial system doesn't work.
Yeah, exactly. The world shuts down. Yeah.
Yeah.
Well, Elijah, as we're wrapping up, is there any advice you would give to our listeners who are trying to understand AI, who are just trying to get a grasp on what is this, how can I use it? What advice would you give to these people?
Oh, look, there's so many resources out there. I always think there's a lot to be gained by doing. So generally don't maybe sit there and try to, understand the sort of hardcore theory behind statistical learning theory. That can come later. It's sort of easier maybe just to read blogs, jump on Less Wrong. Neil Nander at Google, he runs the MECHINT team there. He has some amazing blog posts. And then just start coding and start seeing, AI is an empirical trial and error, throw things at the wall, see if it sticks discipline. Mm-hmm. That's the kind of fundamental distinction between AI from 1956 until about 1990 or the early 2000s, because people tried to theoretically formalize and then build these formal systems that didn't really do anything. Mm-hmm. Well, that's not quite true. But it wasn't until then, kind of like with Google Translate. Google Translate started off with dictionaries, trying to sort of learn the sort of map, and then they just threw that out and they said, let's just learn a trial and error. So jump onto Colab, read around, don't be afraid to ask dumb questions.
Love that.
And just talk to people. But it's so accessible now, especially with large language models. You can very quickly get it to explain what's going on.
I love that.
As we're wrapping up here, if our listeners are wanting to follow you and what you're up to, your upcoming papers, etc., what is the best place to do that?
Probably just Google Scholar at the moment. I've got to fix my website.
The eternal curse of anybody in anything tech facing.
I'm thinking, seeing if I have the risk appetite to let Claude's coding agent, which for people don't know, that's where you essentially let Claude take control of a subdirectory and start to update the region. You essentially just talk to it.
Have at it.
Yeah. And then maybe see if that one, see how it went updating someone with a similar name to me, but not quite me. And then if that went well.
Nice. Let us know how that goes.
And my contact details are probably all over the internet. They're probably on the dark web. So feel free to reach out if you've got any questions.
Give you a call. If we happen to stumble across your number on the dark web somewhere, hey, this guy's on the podcast I was listening to.
Well, thanks, Elijah. We'll stay in contact. Thanks for coming on. This was great.
Thanks very much, guys. Very much appreciate the opportunity.
Yeah, thank you.